So in the previous lecture, we have explained that we are doing secret codes, the chapter number 15. The process of converting a message into a string of numbers or letters according to some rule that only the sender and the recipient know is called encoding, and the process by which the message converts back to the original one is decoding. For example, we have set a rule that we substitute 01 for A, 02 for B, 03 for C, and so on to 26 for Z. And then we have written this message and then we have converted it into the code. So then uh, the in nowadays world, the secret codes we use are called RSA codes. Okay. And these are based on the prime numbers and then congruence theory, which we have did in previous chapters like 13 and 14. Now, what makes their security based is the thing that the computers would need to identify that what computers cannot do. And something from there is we can say that, let's say we have two primes. So one this and then other one this, their product is this one. So this you can calculate by any calculator in seconds. But if you have been given this product and asked to find its prime factors, it would take the calculators much longer. So what we mean is that we can if we take two primes with say with 200 digits each and we calculate their product and keep P and Q secret, but tell your computer their product. Like consider the most powerful computer in the world. It would take that computer like at least several centuries to find out what P and Q are. So that's what computers find difficult to do, and that is called prime factorization. Factorization. Okay, perfect. Now we will talk about the topic RSA codes. Encoding. How we encode these messages. Perfect. So here are some encoding and decoding processes for RSA codes. So let's say we choose two large primes. Prime numbers P and Q and multiply them together to get n is equals to PQ. We also find P minus 1 into Q minus 1 and choose a large number E, which is coprime to the product of P minus 1 and to Q minus 1. Okay. We then make public the numbers N and E. We then make public, we tell people the numbers N and E, but keep the values of P and Q secret. but keep the values of P and Q secret. So we shall illustrate the discussion with the values. So let's say we have P is equals to 37, Q is equals to 61, then N is their product, which is 2257. And P minus 1 into Q minus 1 is 2160. E is 11. E is 11. So remember, to ensure the security of the code, one uses primes with around 200 digits, but these primes will serve for the illustration purpose. Okay, so you should write that to ensure the security of codes, one uses primes with around 200 digits. This is just an example. So now the pair N comma E is called the public key. Everybody knows. Okay. Anyone who wants to send us a message can use the numbers N and E in the following way. So you can say anyone who wants to send us a message can use the numbers N and E in the following way. First, they convert their message into a string of numbers. Numbers by some process. Such is the one given above. We have discussed in previous lecture above 01 for A and so on, etc. Then they then break up this string into a sequence of numbers. Then break up. Let's write it on a new line. Then break up this message not message, this is string into a sequence of numbers with fewer digits than n. For example, with p comma q is above, or for example, p is 37 and q is 61. The message 15.1, the message 15.1, that is this one. (15.1) would break up as the sequence. So let's write the 15.1 again, but like break up would be broken up is the sequence. So the 15.1 was combined like this, but you just have to remove the commas. Now I am writing it in a breaked up shape. So we are making it pair of 3. Okay. So if you remove all these commas and combine these, it will be the 15.1. And the actual message was small brain is the culprit. So the message now is a sequence of numbers. So the message now is the sequence of numbers, and we call it M1, M2 up to MK. Okay. The next step is to encode this message. Encode this message. To do this, the sender calculates for 1 less than or equal to I less than or equal to k the value of ni, value of ni, where this ni is nothing but is congruent to mi power e mod n, and it is between these two numbers. Okay, this can be done quickly on a computer using the method of successive squares described in example 14.3. The encoded message is the new list of numbers. The encoded message is the new list of numbers, say n1, n2 up to nk, and this is the message that is sent to us. Okay, so for P is 37, Q is 61, Q is 61, M1 okay, no, not this one, but like the example above. This example we are talking, yeah. So in the example above, M1 is 191, which is 1. This is M1, this is M2, and this is MK. Okay, so N is 2257 and E is 11. Using the method of successive squares and using the method of successive squares, we have 191 square is congruent to 369 mod 2257. 191 power 4 is congruent to 741 mod 2257, and 191 power 8 is congruent to 630 mod 2257. Okay, and hence 191 power 11 is congruent to 191 power 8 power 2 plus 1 which is congruent to 630.369.191, which is congruent to 2066 mod 2257. Here, hence, N1 is equal to 2066. Similarly, we find that N2 is 483 and 3 is 914 and 4 is 1808 and so on. So the encoded code message is, so the encoded message is 2066 483 914 1808 and so on. And this is the process by which we encode any message. Okay, so this is how we encode the messages. Okay, let's try and decode this message now. Let's try and properly decode this message. Okay. So now we will do the decoding. Which is very important. So once we have received the message, we have to decode it. In other words, given the received list of numbers, N1 to Nk, we need to find the original numbers M1 to Mk, where we know that Ni is congruent to Mi power E mod N. But Mi is just the solution of the congruence equation. But Mi is just the solution of congruence equation. X power E is congruent to Ni mod N. And by proposition 14.3, we have solved such congruence equations. We have solved such congruence equations. Since E has been chosen previously, chosen to be co-prime to P minus 1 into Q minus 1, we can find the Euclidean algorithm you can use to find the Euclidean algorithm to find a positive number integer d such that de is congruent to 1 mod P minus 1 into Q minus 1. Then the solution to the congruence equation x power e is congruent to ni mod n is nothing but x is congruent to ni power d mod n. And of course, this solution must be the original number mi, and hence we recover the original message m1 to mk. Okay, perfect. So this is the decoding process, right? So in the above example, E is 11 and P minus 1 into Q minus 1 is 2160. And since N1 is 2066, so to recover the first number M1, the original message, we need to solve the congruence equation. X power 11 is congruent to 2066 mod 2257 And by Euclidean algorithm, we have 1 is equals to 1571.11 minus 8.2160. So D is 1571. Okay. We then use the method, the successive square, to calculate that 2066 power 1571 is congruent to 191 mod 2257. So M1 is 191 of the original message. Similarly, we can recover M2 up to okay. Similarly, we recover M2 up to MK. So to summarize, to encode a message, we raise each of its listed numbers to the power of E for encode, and work out the answer modulo n. And to decode a received message, we raise each of its listed numbers to the power of D for decode, and work out this modulo n. Now let's decode a new message, still keeping the above values of P and P, Q and E. So let's decode another message. So let's say this is an example. And P is $37, Q is 61, N is 2257, E is 11. Okay. Now you are relaxing on your hotel balcony in Monte Carlo, sipping a cola, when your laptop beeps and the following strange numbers arrive. So what are the strange numbers? The numbers are 763281034 559 2067 2028 798. Remember, we have SAM, P, Q, N, and E. Okay, and these are NIs. At once you spring into action, getting your laptop to solve the congruence. So what congruence we solve? Congruence equations. We solve these congruence equations as follows. Quite tricky, and lengthy, so bear with me. We are saying x power 11 is congruent to 6763 mod n. We have the value of n, so we will write only n, and we also have the value of e, that is 11. So let me just write it here again. E is 11, n is 2257. Okay, and this goes to x congruent to 763 power 1571 mod n, and this is nothing but x mod n is 251, which I guess is m1. Similarly, x power e is congruent to 28 mod n, and this will go to x congruent to 28 power, and if you remember, the value of d is 1571, which is same. Yes, so the value of d is same also, so this value is d mod n, then x mod n is nothing but 521, which is m2. Similarly, x power e is congruent to 1034 mod n, then x is congruent to 1034 power d mod n, and this is nothing but x mod n is 180. M3, and we're still solving. So 5, 5, 9. So now we are here. Mod n goes to x congruent to 5, 5, 9 power d mod n, and this is a solution to this, which is equal to 506, and can be said that it is M4. X power e is congruent to 2067 mod n. This goes to x is congruent to 2076, actually 67. Yeah, power d mod n, then x is mod n equals to 091, and this is M5. Two remaining equal. Number is 2028 congruence to 2028 power d 805 congruence to 798 power d is equal to 04. So this gives the decoded message is the following string of numbers. What numbers? So 251 521 180 506 091 805 04. Okay. Using the original substitution, using the original substitution, 01 for A, 02 for B, and so on, you finally translate this message to the translation of this message is YOUREFIRET. You are fired. So this is how the RSA code encoding and decoding works. In the next part of this lecture, this chapter, we will talk about little about security and then some history of these codes. Thank you so much. Bye.